Okay guys, so as I gave you some homework in the past lecture, I'll be continuing on from that only. So yeah, so if you look at the hybridization of nitrogen here, it is clearly sp3, so it follows the Brett's rule. Okay, so now we'll look into the application of uh, resonance hyperconjugation and inductive effect through heat of hydrogenation. So heat of hydrogenation is nothing but the amount of heat released during hydrogenation of the compound. So if we have if we draw energy level graph of all these compounds, then you can see that this is experimentally proven fact that the amount of heat released when we hydrogenate this compound is 217, for this is 120, and for this is 117. Why is the reason is because this compound is obviously, you can see for these two compounds, as we have seen in the past lectures, that obviously this compound is a cis one and this is a trans one. So the stability of cis is less than the stability of trans. Why? Because of steric hindrances of these two bulky methyl groups attached near to each other, right? Okay, so and how are we comparing the heat of hydrogenation among three compounds? Means they are just three random compounds, are they? No. Why? Because when we actually hydrogenate it, the structure or the organic compound we get after hydrogenation is butane, and same for this case and same for this case. Hence we can compare the heat of hydrogenation for all of these. And why this less stable than the remaining two? The answer is simple. The number of alpha hydrogen in this and these are 6, while the number of alpha hydrogen are only 2 for this. Hence this structure is more unstable than these two structures. Why? Because of less number of hyperconjugation or the less number of alpha hydrogens. Okay, so the heat of hydrogenation is inversely proportional to stability for isomers. What is isomer? These three are the isomers of butene. We will look into the intricacies of what is isomerism and all of that in upcoming lectures, but for now you can just remember that these three compounds actually, when we hydrogenate, comes to the same compound. Or you can just forget about isomers for now. You can just remember it for the note making purpose. Okay, so just remember the two rules for heat of hydrogenation comparison is this holds for isomers, and product formation should be the same when we hydrogenate it. Okay, so the second point is more the number of pi bonds, more is the heat of hydrogenation. It's that simple. Why? Because when we are attaching more number of hydrogens to one more covalent bond or one more bond, as was in some other structure, which is resulting into the same product formation, then obviously the heat of hydrogenation would be more. This is pure common sense. Okay, so now let's look at the third point, which is nothing but the heat of hydrogenation released per mole of hydrogen is inversely proportional to the heat of hydrogenation of the overall compound. So let me write this, that heat of hydrogenation per mole of hydrogen is inversely proportional to the heat of hydrogenation. Okay, so what do I mean by it? Obviously I will take some example and explain you, and this would always be the case when I am teaching, because I teach by example and not by concepts, especially in organic chemistry. Okay, so amount of heat released for this thing is, as in the previous example we saw, that this is 120 kilojoule per mole and this is 232 kilojoule per mole, but per mole of hydrogen we can actually divide it by 2, divided by 1, so per mole it is less than this compound. So the heat of hydrogenation per mole is inversely proportional to the heat of hydrogenation of the overall compound. Okay, so now let us look into the stability order of some of the carbon compounds, and using that we will be comparing the heat of hydrogenation in few minutes. Okay, so we have to just tell the stability order for this one, this one, and obviously this one. So what is the stability order? Okay, for your information, or I'm telling it too earlier than the course duration, but I hope you should know it by now. That's why I'm telling it. So this is a conjugated alkene, this is an isolated, and this is a cumulative. Okay, so stability, tell me the stability order. So this is involved in resonance, so this would be the most stable, and for these two just calculate the number of alpha hydrogen. Number of alpha hydrogen for this is just 2, and for this is how many? 1 2. So what else? So as the number of alpha hydrogen are same, so what we can tell about the stability, if you have observed clearly or carefully, then actually, so how do we compare the stability when the two of them have the same amount of alpha hydrogen? So why not you just make the hyperconjugating structure and then analyze. So if you make the hyperconjugating structure for this, we will have something like negative charge here and double bonds are here, so it will result in more number of hyperconjugating structures. Why? Because this negative charge can either go here or here on this compound, on this one, or on this one, right? But on the other hand, this would have a conjugating structure something to this one, so it would not result in more number of hyperconjugating structures. Hence, even if the number of alpha hydrogen is same in both the compounds, this is more stable than this one. Okay, so these are the type of examples you might face which are tricky ones, and from the exams perspective, so you need to practice a lot on these type of examples to get more hands-on experience and experience. Yeah, so this is the order of stability, and for this compound, what is the for the this compounds, what is the order of stability? Again, the number of alpha hydrogen for this is only 3, and for this it's 6. No need to compare the hyperconjugating structures. Okay, so now we address the main thing. We need to compare the heat of hydrogenation for the following compounds. Compare the heat of hydrogenation. Okay, let us start. This one, this one, or just pardon me for that.